So I was working on ET quantification, but like the preparation for it. So oftentimes within modeling ET, we can't really remotely sense actual evapotranspiration, so we use a model for it. So just to start, I'm sure everyone's seen this picture, some version of it of the water cycle. So ET is evaporation and transpiration combined. And then we shorten the word to ET. Transpiration is evaporation that occurs from the plant, and then evaporations from the soil surface or from the water surface. So within the realm of irrigation management, oftentimes our goal is to replace ET lost with irrigation. Um, this can pose an issue though when we're trying to quantify ET on like a field scale or a plot scale, which is oftentimes what farmers manage at, because our ET quantification methods generally occur at the basin or the sub-basin scale. And there's good reasons for this. Some of it is because the methodology isn't appropriate for a plot scale, and some of it's because the costs associated with quantifying ET are large. So it's sometimes not justifiable to do on a plot scale or field scale. So there's sort of this gap that exists that is possible to bridge though. So the model that I worked on trying to prepare data for is the two-source energy balance model. And so it quantifies ET through an energy balance, not through a water balance. And so the energy balance is at the top of the screen there. It's net radiation equal to sensible heat flux plus soil heat flux plus latent heat flux. Sensible heat flux is the energy that is transferred from the surface into the atmosphere. So heat flux is the energy that's transferred from the surface down to lower layers. And then latent heat flux is the latent heat of vaporization. So that's the ET we're trying to get after. And so this model sort of routes the radiation from two sources, which is the soil and the vegetation. Um, and then it calculates G as a percentage of Rn in a model. Calculates E, or pardon me, LE is sort of the leftover. Um, So here's the inputs that the model requires. And so there's a lot of legwork to do to get your ET numbers. And so what I wrote in Jupyter Hub was code to find the biophysical properties. The weather data, oftentimes you can get just directly from a weather data station. So it's these biophysical properties that are the most difficult to get after. And so this is I'll get into that in a second. So this is the gathering. So in the gathering data phase of the code, there's a little bit of legwork to do before you even run anything in the code. The first off, obviously, is you need to select your satellite and your date range. Just for the default, and I try to make the code very versatile so that anyone could use it for running tsub at any location on Earth. But I just defaulted to my research project that I'm working on. So the satellite I chose was Landsat 8, and the date range was the 2022 growing season. So I selected a weather station that was close to there to find the weather data. So you have to upload the weather data and then upload a file structure for the outputs. And within the code, I made comments and everything so that it's very easy to figure out what's going on so that anyone could use it for any location. And then, of course, you need to set up your GPS location and then finally run the code. So this is the pre-processing for the weather data. Is find and upload it like I mentioned before, and then change your desired column headings in section 4. And there's comments throughout each section so that you know exactly what to do. In section 1.1, which is the GPS coordinates, you first needed to select a point of interest. And then if you want to, you can crop the entire Landsat image down to sort of an area of interest. That's optional though. You can just run it over the entire Landsat image if you'd like. So this is the field that I chose. It's the one that I did my research data on. So this is in Vernal, Utah. It's the research field at the USU campus there. The big like green center area, that's the actual field. Up here is the campus building. So they're obviously shot up differently than the field does. Over here is a detention pond where they get most of their water. And then up here is kind of just a dirt lot where they store a lot of their equipment. So the center, like green area is the one area we'll be focusing on. So next in the code, I set up gathering all my data from the Landsat. Um, and I filtered out cloudy days. But this is wanted to show this because this is just where you can change your bounds of what data you want to collect. And then moving on to the biophysicals, now that we've collected all our data. The first biophysical we're going to look at is fraction of cover. And so there's a developed relationship between vegetation index and fractions of cover that's pretty standard to use. The vegetation index that's typically used is NDVI, so that's the one that I used. And so um, here's sort of the results. So what each cell does for finding each biophysical property is it goes through and it loops through all of the Landsat 2 images that you've selected for your date range, and then it applies the calculations to them to find fraction of cover, and then it downloads them all as .tif files, because that's the format that PyTsub likes to have. But you can also transfer those into ArcPro pretty easily and mess with them if you need to. Um, and so I just grabbed a screenshot of it generating the TIF file on the last image and then the output image. It uses the minimax of the display image uh, as the color scale, so that is kind of coordinated to itself. And then I also set it to display just the earliest image within the year, but you can change that if you want it to display a certain date. The next biophysical property was leaf area index. And so I had, through my research, I had a site-specific location that related fraction of cover and LAI. So to use this, you would need something similar to calculate LAI or another way to calculate LAI. Um, and so the default that I put in was my equation of LAI is 6 times the fraction of cover, but that can be changed super easily. I tried to make the code very versatile. So just grab another screenshot. Here's it again, generating the TIFF file, and then displaying the first image. Again, that center portion where it's kind of darker is the area to look at because that's the area that's actually the field. The next biophysical property that T-sub requires is a crop height. And so there's been success finding crop height from different vegetation indices. The vegetation index I used was the SAVI index. Um, and again, it's a site-specific equation, but you can change it. I put a comment in so that you know when to change it to a different equation if you, oh, sorry. So if you want to use a different equation, you can. So here's another screenshot I grabbed. So again, it's just generating the TIF file so that you can upload it to TSub or upload it to ArcPro, and then the image that it displays so you can kind of check your work. And then the radiometric temperature or the surface temperature is required by TSub also. Fortunately, Landsat provides this through band 10 with pretty simple calculations. It just has an offset and a multiplier. So here's the uh, code being ran through that for that cell. Again, it's just generating TIF folder and saving it to the set location that I specified. And then it generates the map. It's pretty, I guess, confidence boosting in that map since we know the center of the field is the actual portion where they're growing crops. And so that's the cooler colors. And then the concrete, parking lots, and buildings are the hotter colors there. So that makes sense. And then finally, the weather file that we needed to upload, you do have to process through that. So I have it loop through every single Landsat image, and it selects the date from that image, and then it finds the closest solar noon because that's when about Landsat flies over. If you're on daylight savings time, if you're on standard time, it's really closer to actual 12. Um, so it extracts from the CSV file the date and timestamp that's closest to that with the specified headers of which data you want to extract. And then it builds a new CSV file with that information so that you can use that when running the model. Yeah, that's all I looked at for it. Thanks.